Hi all, welcome to chemistry. This is our first unit. It's called the physical behaviors of matter. Today we're going to go over one of the fundamental parts of chemistry, and that's knowing how to calculate error. Now, in everything we do, we know that there's going to be a percentage of error, and in chemistry we're able to calculate that. Now, if you took earth science before this, then you've already done percent error and you know the formula. This will just be a refresher. If you haven't, well, welcome. All right. So, one thing I want to let you know is that any formulas that we talk about in this class can be found on our reference table. Now, the reference table is under the resources in our Google Classroom, so you can go and download your copy there, or you could just Google chemistry reference table, and the first link would give you the actual PDF file of it. I suggest if you have a if you have a printer at home, you should print it out just so you can mark it up. And it's really good to have in hand than anything else. But if you have to use the computer or your cell phone or your iPad for it, that's perfectly fine. So let's go ahead and get started. Now, this is if we were in class today. So our learning target would be I can calculate percent error by distinguishing between accuracy and precision. Now, at this point in the lesson, I'm going to ask you what your definition of accuracy and precision is. How would you define it, right? And also in this point in your notes, you would see that you have a reading. So at this point, keep saying this point. At this point, go ahead and pause and complete your reading. It should take you about 5 to 6 minutes. And then there's 2 test-related questions. So you should be back from your reading at this point. This is what our agenda looks like. We're going to talk a little about the reading, the intro. We're talking about accuracy and precision. Um, you should have already done your reading, and then we'll go to a percent error practice problem. Now, we will do percent error today, but we'll practice it a whole lot more tomorrow. So, like I said, how would we define accuracy and precision? Go ahead and do your reading. Now, this is an example of accuracy and precision. I want to see how you break it down, and I'll obviously help you with it, right? When it comes to, let's go back a little bit. When it comes to accuracy, accuracy is hitting it directly on the dot, right? If you were meant to get 100, you got 100. If you were meant to get 50, you got 50. That is how we are accurate. We hit the bullseye right in the center, right? Or we we made that free throw shot right into the hoop, right? We are being accurate. We are getting what we were supposed to get. You hit the goalpost. You hit your free throw, right? You are making sure you're hitting that target every single time. That's how we are accurate. Now, when it comes to precise, it means that you may not be hitting your target all the time, but you are close. Your range is very close, right? So that means instead of you dunking it into the basket every single time, you're hitting the rim, you're hitting the backboard each time. You're being precise, you're not being accurate. So precise means you're getting around the same range, but you're not hitting the target that you were supposed to hit. So here's a practice problem. We could try this out, right? So we have Cheryl, Cynthia, Carmen, and Casey. They take target practice in PE, assuming that they were all aiming at the bullseye, which is the center of the dart. Match each target with the proper description. Now I'm going to do this with you. So the goal was for us to hit the target, and the target is right in the bullseye, right in the middle, right? So if we look at all of these images, the only person who was successfully able to do that is Carmen, because Carmen hit the middle every single time. So we would give Carmen that she is accurate. But Carmen is also precise because Carmen hits the center dot every single time. So yes, you can be accurate and precise at the same time, or you can be accurate and not, yes, at the same time. But you cannot be precise. I'll get back to that thought. But like I said, you can be accurate and precise. So Carmen would be A, Now, if we look somewhere else, even though let's look at Casey for a second, Casey is not hitting the bullseye. She's not hitting the bullseye. But Casey's dots are close together. So that means that Casey was precise, not accurate. And you can be precise and not accurate. But you can't be accurate and not precise. Right? So, she was precise but not accurate. So, Casey would be C. So now let's go back to Cheryl and Cynthia. Cheryl, we see her dots are all over the place. But then we have Cynthia who has like one dot here, like right at the edge of the center, right? So Cheryl, I would claim that Cheryl is neither precise nor accurate. Her being at the edge doesn't help. We want her to be directly at the center. That would leave Cynthia with being not precise, but one piece of data accurate, because we do see that one dot has ended up in the middle. So that was that example. So we're going to do this as a breakout room. If you're in the live video, you'll understand. If you're not, take it and try to see if you can figure this out. A student is given a rock that is known to have a mass of 436.8 grams. She measures the mass of the rock 3 different times with the following results: 460.9 grams, 461.4 grams, or 459.0 grams. What can be said about her precision and accuracy? I want you to take a moment, think about that, and let me know when we have the live class. What do you think? We have another problem independently, but we're going to do this together, obviously. We have this practice problem. The following data was collected during a lab experiment. The density of the cube should be 10.8 grams per milliliter. Is the data accurate, precise, both, or neither? Justify your answer, right? And they give us the trial. They give 6.2, 6.3, and 6.5. Now, for the data to be accurate, we should be hitting the density at 10.8. However, once we conduct our trials, we are nowhere close to 10.8. So that means instead of us being accurate, we are precise, because our numbers are literally like 0.2 or 0.1 digits away from each other. We have 6.2, 6.3, and 6.5. They're all within the same range. So as long as we're in the same range, we are precise. But because they are not 10.8, they are not accurate. So this question is another discussion question that I'm gonna ask you during the live class. How does accuracy and precision how are accuracy and precision important in determining percent error? Right? Why do you think that's important? Why do you think they're related? When we have the live class, I want to see if you guys can give me the answer to this. So that brings us back to percent error. Now, percent error, the density, the formula can be found on table T of your reference table. It is the last table. That's where all your formulas can be found. And the formula gives us 2 variables. We have the measured value and the accepted value. When it comes to notes, if we're in class, I would say have your MV and your AV. You can go ahead and call it measured or accepted. It's up to you. But as long as you know that these are your variables. Now, this is the formula. We have measured minus accepted divided by the accepted value, absolute times 100. Now, what do I mean by absolute? The absolute, do you see these 2 marks on the sides? That means the absolute value, meaning that our percent error will never be negative. Our percent error will never be negative. We're always going to take the positive. Now, anytime you guys ask us that question, you can ask Mr. Shorts this. I will always say, have you ever seen a negative percentage in your life? No. So, never, never, never. Percent error can never be negative. All right, so this is our formula. Simple formula. It is the first one on the reference table. Actually, no, density is the first one. I think it's the third one on the reference table. The third one on the reference table. And it's the easiest ones to remember. So we have this class practice, and we're going to do this together, and then So, you have a couple of more practices in your notes, and then you should be good. Tomorrow, we're going to practice a whole lot more. I always believe in practice. So, our sample problem is in a lab experiment, you are told by your teacher that the actual or the accepted amount of sugar in a can of Coke is 39 grams. You experimentally determined it to be 40 grams based on your own data and calculations. What is your percent error? Now, one thing I always believe in is pulling out your information. You should be able to read a problem and say, this is an information that I need. Now, if you can't do that, we need to talk. But you should be able to pull out information, a variable, right? So they tell you something. They tell you your accepted amount is 39 grams. I know that here. I'm going to highlight that in green. Sorry for that noise in the background. Um, and then they also tell us we experimentally determined it to be 40 grams. So I'm going to highlight that in cyan. So we already know two information. We know two things they give us in this problem. And we also know what they want us to calculate, percent error. We need to be able to pull this out of every problem we do in chemistry, in math, anything. We need to be able to know that they want us, what they want us to do, and the information they're giving us to do so. So, looking at the problem, I know that our accepted is 39 grams, and I know that our measured is 40 grams. Now, I always require you guys to write the formula. It makes it easier on yourself to always have the formula on the paper. So here's my formula. Percent error equals accepted minus measured divided by accepted times 100. Now, because I'm using the computer, I can't really write the absolute values sign on it, but I'll figure that out. Also, one thing I wanted to mention, your measured and your accepted can be flipped around. Math rules. Remember, your accepted minus your measured must be positive. So that means if you have to flip it around, that means you have to flip it around. That's perfectly fine. All right. So I'm going to go ahead and plug in the information I know. I know that my accepted is 39 and I know my measured is 40. So everywhere it says accepted, I'm going to put 39, and where it says measured, I'm going to put 40. Right? So that gives me 40 minus, it actually should give me 39 minus 40 divided by 39 times 100. But math rules, so I'm going to do 40 minus 39 divided by 39 times 100. I'm good. I'm going to do my subtraction first, pandas. Always remember that, subtraction first. So I get 1 over 39 times 100. I'm then going to do my division next. So I'm going to do 1 divided by 39. 1 divided by 39 is not 39. All right, 1 divided by 39 is not 39. Use the calculator. Just use the calculator. So 1 divided by 39 gives us 0.0256. I want you to stop at 3 to 4 decimal places. Right? 3 to 4 decimal places. Do not write the whole number. Just 3 to 4 decimal places. Times 100. And obviously when we multiply by 100, some of you can do this in your mouth, some of you in your head, some of you can't. That's perfectly fine. Use the calculator. You're going to need it. And you get 2.56 as our percent error. And that's it. Easy peasy lemon squeezy. All right? And that's how we do percent error. That is what accuracy and precision is. And this is how it's related to percent error. So we will meet up in the live session and we'll talk about this and we'll get more practice today and tomorrow. If you have any questions, please feel free to contact me or Mr. Shorts, and we will most definitely be glad to help you. All right, guys. I'll see you later. Have a good day.